Modern large language models function as massive infrastructure. Serving these parameters requires thousands of hardware accelerators running continuously at their thermal and power limits. Memory bandwidth and the energy cost of data movement dictate the performance envelope of modern inference. Raw arithmetic throughput has outpaced the hardware's ability to feed the processors. Reducing the number of bits stored and moved through the memory hierarchy directly attacks this cost. Quantization addresses the specific physical constraints that prevent high-parameter models from running at scale. Hardware measurements confirm a massive energy gap between compute and memory. Fetching data from off-chip HBM costs roughly 500 picojoules, nearly 1,700 times more energy than a standard INT8 arithmetic operation. Expanding context lengths amplify this data movement. While model weights remain a constant load, the key value cache, storing attention keys and values for every token generated, adds linear growth to every request. This chart tracks that scaling for a 7 billion parameter model. At a 128K context length, the KV cache drives total memory traffic to 78 gigabytes per generated token, a 5-fold increase over shorter sequences. These figures explain why latency plateaus despite faster processors. True optimization requires a direct reduction in the total bytes moved per token. Quantization translates neural network tensors from adaptive 16-bit floating-point representations into rigid, low-bit integer formats. Floating-point formats use variable spacing to maintain relative precision. Integers replace this with a fixed grid, where every value is evenly spaced. This fixed bit width forces a trade-off. Allocating bits to increase a number line's range simultaneously reduces the resolution between individual steps. Engineers use calibration to resolve this tension, analyzing the model's actual activation ranges to determine exactly where to place the discrete integer grid. Neural networks tolerate precision loss because weights encode relative influence rather than exact physical values. The models effectively absorb the bounded approximation error. Overparameterization provides further protection. In larger models, redundant weights allow the system to maintain signal integrity even as individual parameters are coarsened. Deploying these models requires choosing between symmetric and asymmetric quantization schemes, a decision that dictates the architecture of the hardware's arithmetic logic units. Symmetric quantization pins the grid at 0, simplifying the linear algebra for fast execution on bell curve weight distributions. Asymmetric quantization uses a shifted window to preserve bits for skewed data, though it adds mathematical overhead to the inference runtime. Signal-to-noise ratios define the limits of this compression. At INT8, noise is 16,000 times smaller than the signal. Pushing to INT4 reduces that ratio to 1 to 49, requiring careful grouping strategies to prevent accuracy collapse. Choosing a quantization scheme determines how the hardware executes the model's operations. The right balance of speed and statistical density ensures the model meets performance and accuracy targets. Scale your deployment by targeting memory bandwidth as the primary constraint, precisely mapping the integer grid to your data, and aligning your choice of symmetric or asymmetric schemes to the underlying tensor distributions. Solving these physical and numerical trade-offs is what determines if a model scales to millions of users or fails under the weight of its own serving costs.